Scalars and vectors are two different types of entities that are essential to the quantification of physical phenomena. The big difference between scalars and vectors is that to describe a vectorial quantity, you need to provide information about the direction in space. This direction in space is an integral part of what a vector is. The information about the direction in space makes it impossible to describe a vector with only one real number and measurement unit. However, a scalar is a quantity that can be described with one real number and a measurement unit. An example of a scalar is the mass of an object. A particular mass could be quantified as 434 grams. Other examples of scalars are time, length, temperature, percentage of maple trees in a particular forest, or the number of cows in a field. To describe a vector, you need to give the size of the vector, called its magnitude, and a direction in space, or any information that could lead to the evaluation of the magnitude and the direction in space. Examples of physical quantities that need to be described as vectors are velocity, displacement, and forces. A particular velocity could be described as 100 kilometers per hour towards the south. Both types of quantities will appear in equations that will summarize mathematically the relationship between them. To differentiate between the scalars and the vectors, the variables that are vectors will have an arrow above their names. On the scalar side, the letter m is often used to represent the mass of an object, and the Greek letter theta for an angle. The letter v, with an arrow above it, could represent a velocity. Unit vectors are vectors with a unitless magnitude equal to 1. Their variable names use the hat instead of an arrow. The absolute value of a quantity is symbolized in equations by placing the quantity between vertical bars. If the quantity is a scalar, the absolute value essentially removes the sign of the scalar. A negative scalar value becomes positive, and a positive scalar value does not change. For example, the absolute value of minus 2 meters per second is 2 meters per second. If the same symbolism is applied to a vector, it is the information about the direction in space that is removed. All that is left is the magnitude of the vector, which is, on its own, a scalar. The variable name of the vector without the arrow is often used to represent the magnitude of the vector. As an example, let us work with the vector velocity 100 kilometers per hour towards the south. Please notice in passing the abbreviated version of the information about this vector. It is customary to list the magnitude of the vector, followed by a short description of the direction written inside square brackets. If the vector v is 100 kilometers per hour south, then its absolute value, which is the same thing as its magnitude, is simply 100 kilometers per hour. Please note that once the vector v is being used, the unit vector that uses the same variable only keeps the direction but changes the magnitude to 1. Let us consider the product of scalar small a with vector capital A. The result is itself a vector. The magnitude of the vector product is the product of the absolute value of scalar small a with the absolute value of vector capital A, which is the same thing as the magnitude of vector capital A. The direction of the vector product is the same as vector A unless the scalar small a is negative, in which case the direction would be reversed. For example, if we have two scalars m and b and a vector v, then the magnitude of the product of m and v is the product of the absolute value of m, which is 34 kilogram, with the magnitude of v, which is 10 meters per second. This product is 340 kilogram meter per second, which I have explicitly expressed with power of 10 to show that the answer should have two significant digits. Since the scalar m is positive, the direction remains towards the north. For the product of b with v, the product of the absolute value of scalar b, which is 2, with the magnitude of vector v, which is 10 meters per second, gives an answer of 20 meters per second, which also needs to be expressed with two significant digits. Here, however, the direction of the vector product must be reversed to south because the scalar b is negative. You know how to add scalars since primary school, but how do you add quantities that carry information about a direction in space? Well, by visualizing them as arrows. An arrow is a directed light segment with a tail and a tip. The orientation of the line gives information about the direction in space, while the length of the arrow is made proportional to the magnitude of the vector. A second arrow with the same length and that is parallel to the first arrow represents the same vectorial quantity regardless of where it is drawn. Let's say that you want to add vector A to vector B. Both vectors need to use the same measurement units, just like in additions of scalar. It is meaningless to add 3 kilograms to 5 meters. To visualize the arrow that would represent the sum of vector A and vector B, you need to redraw these two vectors so that the tip of A is at the same location as the tail of B. The arrow with its tail on the tail of A and its tip on the tip of B is the sum of vector A and B. Note that if you want to draw the vector B plus A instead, then the tail of vector A would have been placed at the tip of vector B, and the vector B plus A would have been drawn from the tail of B to the tip of A. We have drawn the figure of a parallelogram. Since vector A plus B is the same length and is parallel to vector B plus A, they both represent the same vectorial quantity, so they are equal. We can say that A plus B equals B plus A. Let us start with the same two vectors, but this time we will subtract vector B from vector A. Using something reminiscent of what we can do with scalars, we will transform a subtraction into an addition of the negative of the quantity. We know that multiplying the scalar minus 1 with vector B will not change the magnitude, but will reverse the direction. So the vector minus B will look like an arrow with the same length as vector B, but pointing in the opposite direction. From now on, we will follow the procedure to add vectors. We draw vector A and vector minus B with the tip of A at the same location as the tail of minus B, and the arrow created from the tail of A to the tip of minus B represent the vector A minus B. Similarly, we can draw the vector B minus A. We have created identical triangles. The length of A minus B is the same as the length of B minus A, but the two vectors are in opposite direction compared to each other, which means that the vector A minus B is equal to the negative of the vector B minus A, an expression reminiscent of what we would expect if all quantities were scalars. This concludes our first glimpse at the brand new quantity that are vectors. Next, we will look at a different way of expressing a vector that will eventually make it easier to work with vectors in equations. This will be the subject of the next installment.